Nucleophilic substitution reactions are an important class of organic reactions. Both aromatic system and aliphatic system undergo this type of reaction. Now, in this video, we shall be discussing about one type of aromatic nucleophilic substitution reaction, and that is SNAr reaction, or we'll be discussing the mechanism, SNAr mechanism. Now, an aromatic nucleophilic substitution reaction is a replacement of hydrogen or a substituent on the aromatic ring by a nucleophile. Now, this aromatic ring do not usually undergo nucleophilic substitution reaction. It's not very common with the aromatic system. Now, the reason for this is because of the presence of the electron cloud above and below the aromatic ring. This electron cloud above and below the aromatic ring will shield the ring from nucleophilic attack. The electron cloud is negatively charged and the incoming nucleophile is also negatively charged. So when the nucleophile tries to approach the aromatic ring, there will be repulsion. Another reason which can be attributed for this low reactivity of aromatic compounds towards nucleophilic substitution reaction is the presence of lone pair of electron or a pi bond on the leaving group. This will make the leaving group firmly bonded to the aromatic ring, and that also cannot be replaced. Say, for example, if you have an amino group or an OH group, the lone pair of electrons on the leaving group will participate in the resonance. So this is another reason which makes the aromatic ring less reactive or towards the nucleophilic substitution reactions. But there is a way out. We can make it reactive, or we can carry out nucleophilic substitution reactions on aromatic ring by slight variations. We shall see those. Now you can increase the temperature or pressure, that is, you bring in drastic conditions. Alright, very high temperature or very high pressure, or you carry out the reaction under both, that is very high temperature and pressure, or you introduce a catalyst for this reaction in the reaction pot, or you introduce an activating group, particularly electron withdrawing group, ortho or para to the leaving group. Okay, when that is done, the substrate will undergo nucleophilic substitution reaction very easily. This is usually seen, this particular point is used very frequently in order to bring in nucleophilic substitution reaction. That is, introducing an activating group, an electron withdrawing group, to the ortho or para position of the leaving group. Or you can introduce a very good leaving group which will easily leave the substrate, and then a nucleophile can come. Another way is introduce a heteroatom to the aromatic nucleus, an electronegative heteroatom to the aromatic nucleus. Then also again this aromatic system will undergo nucleophilic substitution reaction. Now, there are four types of aromatic nucleophilic substitution reactions: the SNAr mechanism, or the addition-elimination mechanism, the benzyne mechanism, or the elimination-addition mechanism, SN1 mechanism, and SRN1 mechanism, which has a radical ion as the intermediate. We shall be discussing the first one in this video, that is SNAr mechanism. Now, it's also called as addition-elimination mechanism because addition happens first, followed by elimination. It's a two-step mechanism. First is the formation of carbanion, wherein the addition of the nucleophile happens. That nucleophile will be added to the substrate, and then next is the restoration of the aromaticity of the ring. when a nucleophile is added to the substrate, a carbanion will be formed and the aromaticity of the system will be disturbed. In the next step, a proton will be eliminated and the leaving group will be eliminated, will be removed, and the aromaticity of the ring will be restored. Alright, now this is the first step. You can see here you have the leaving group, and when a nucleophile will approach onto the carbon to which the leaving group is attached. So this is a sort of ipso attack, ipso substitution. That is, the incoming group and the leaving group are on the same carbon. And you can see here a carbanion is formed, and that carbanion is resonance stabilized. Okay, this carbanion with the leaving group and nucleophile on the aromatic ring is called mesenchyma complex, or some books call it as mesenchyma-Jackson salt. Now, once this mesenchyma complex is formed, or this carbanion is formed, later, this is a slow step and this is a rate determining step, alright, the first step. Later on, what happens is the leaving group is removed or is pulled off from the carbanion, and you get the substituted product. Now, this reaction is possible. See here, we have put an electron withdrawing group para to the leaving group. Okay, this electron withdrawing group will stabilize the carbanion. You can see here, among the resonance structures, in one of the structures, the negative charge is on the para carbon, wherein the electron withdrawing group is present. So this electron withdrawing group will pull off the electron charge or the negative charge or the electron density towards itself, making the carbanion stable. Same is the case for ortho position also. So you can see here on the ortho carbon also there is a negative charge on resonance structure 1 and 3. So here also, if there is an electron withdrawing group, then the electron charge density will be reduced, or the charge density will be pulled off from the ring towards the electron withdrawing group. So electron withdrawing groups like NO2, CN, etc. are good substituents which will support or enhance the nucleophilic substitution reactions on aromatic ring. This is a bimolecular reaction wherein the rate determining step or the rate of the reaction depends or is proportional to the concentration of the substrate as well as the concentration of the nucleophile, because formation of mesenchyma complex is the rate determining step. Both the nucleophile and the substrate are involved in the rate determining step or in the rate equation. Now, what are the evidence for this mechanism, SNAr mechanism? Formation of mesenchyma salt is the biggest evidence or the solid proof that there is the formation of this carbanion, mesenchyma salt. Okay, this could be isolated from the picric derivative, and this is called the mesenchyma salt or mesenchyma-Jackson salt. This intermediate could be isolated, wherein both the leaving group, the methoxy group, and the incoming group, the ethoxy group, both are present. So this is the evidence for the SNAr mechanism, that a carbanion is involved and both leaving group and nucleophile are present. That is, it is the addition of the nucleophile and later on removal of the leaving group. Now we shall see few reactions. Here you can see you have a fluorine as a leaving group, NO2 as the electron withdrawing group. You can introduce methoxy group. So just heat it. So the presence of this electron withdrawing group makes the reaction easy. Another example here, ETSH. The ETS minus will be the nucleophile over here. Bromine will be replaced by ETS minus. Another reaction. This is an interesting reaction here. The sulfide ion will be S2 minus. There are two negative charges on, or the charge on the sulfur is -2, on the nucleophile is -2. So here what happens is, the sulfur S2 minus gets added to two substrates. Okay, first it will replace the chlorine to one molecule, and then it will attack another molecule. All right, and so you get this product. In the earlier cases, the nucleophiles had only -1 as the charge on it. Now, here in this example, which I have shown, it is a carbon-carbon attack. See, you can see here, you have both NO2 groups over here, that is both para and ortho to the chlorine leaving group. This hydrogen on the reagent is acidic, and this is removed, and a carbanion is formed, and that will attack this the substrate. In another reaction, the substrate is reacted with piperidine, and the nitrogen on the piperidine acts as the nucleophilic site, and that replaces the chlorine. Here all you can see the hours, the time taken. In the first case it is 18 hours, here you have 16 hours and 120 degrees centigrade, drastic conditions. Alright, another reaction here again, piperidine derivative was taken, and fluorine is replaced. See, it takes 5 days for the reaction to be completed. Now, very important reaction, Shishy-Babin reaction, involves this nucleophilic substitution mechanism, SNAr mechanism. You are treating the pyridine with sodamide. You get aminopyridine, 2-aminopyridine, and see the mechanism here. The amide group attacks this orthocarbon, and then later on this hydrogen proton on the orthocarbon, ortho to the heteroatom, is removed, and then one more proton of the on the nitrogen is again removed, and then negatively charged nitrogen is formed here, and then protonation happens. Okay, and you get 2-aminopyridine. Shishy-Babin reaction is an important class of important reaction in heterocyclic chemistry. Alright, so there also SNAr mechanism is followed. That is addition followed by elimination. Addition by the nucleophile followed by elimination of the proton or the substituent on the ring. Now let us see what is the effect of substrate on this mechanism. The substituent on the substrate has an important role, as we have said earlier. If the substituent is an electron withdrawing group, the reaction will be enhanced. Aromatic nucleophilic substitution reaction will be enhanced. So you can see here the reactivities of the aromatic ring increases when you put azo group or NO group or NO2 group, and the reactivity goes down as the electron withdrawing tendency of the substituent decreases. Okay, when you increase the number of electron withdrawing groups, the reactivity increases. The only thing is that these substituents, these electron withdrawing groups, must be present ortho or para to the leaving group. So you have chlorobenzene over here. This will be, this can be made more reactive towards nucleophilic substitution reaction if you introduce an NO2 group either to the ortho position or to the para position. Now here you have para-nitrochlorobenzene, then you have ortho-para-dinitro-chlorobenzene, then you have picryl chloride. So you have all the ortho positions, and the two ortho position and the para position are substituted by or has got an electron withdrawing NO2 group on it, and so this will be highly reactive. When you look at the reaction rates, you can see here picryl chloride is reacts so fast that it is not able, we cannot measure the rate of the reaction. It's very fast, too fast to be measured. You can see here the relative rate increases as you introduce the electron withdrawing groups to the substituent. Okay. Now this reactivity rate, the reaction rate is for the reaction of the substrate with sodium methoxide and methanol at 50 degrees centigrade, low temperature. Okay, 50 degrees centigrade only. Now, as I said earlier, the position of the electron withdrawing group is a very important factor. It must be either ortho or para to the leaving group. Then the reaction will be very fast. Now, we'll see why is that so. Here, when the nucleophile attacks the substrate, the nucleophile and chlorine, the leaving group, both will be attached to the carbon, and carbanion will be formed. Now, as I had told you earlier also, explained it to you earlier also, this carbanion, this negative charge on the carbanion will be taking part in the resonance, and in one structure you will have the negative charge on the carbon to which the electron withdrawing group is attached. So here you have it on the para carbon. It will be also present on the ortho carbon here. All right. So the presence of the negative charge either on the para carbon, the presence of an electron withdrawing group either on the para carbon or on the ortho carbon will increase the charge dissipation, or the charge density on the carbanion will be decreased, because this electron withdrawing group can easily pull away the negative charge from the ring. Now, if the electron withdrawing group was meta to the leaving group, what will happen? The negative charge will not be present on the meta carbon. So you can see here in these resonance structures, contributing structures, the negative charge is never on the carbon to which the electron withdrawing group is present, that is to the meta carbon. And thus this this carbanion will not be as stable as the carbanion in which the electron withdrawing group is present, para or ortho to the leaving group. That is why the position of the electron withdrawing group is very important. It must be either para or ortho to the leaving group. Now, what about the nature of the leaving group? Now, the leaving group must be stable anions. Okay, then the reaction rate will be increased, because once the leaving group leaves the ring substrate, then it must be stable. It must be stabilized. Okay, otherwise it will be reluctant to leave if it is not stable, it will be reluctant to leave the substrate. Okay, so the order of leaving group ability is fluorine is a very good leaving group on aromatic ring, followed by NO2, OTS, etc., and it goes on. Alright, now among the halogens, you can see here fluorine is the best leaving group, even though it is the CF bond is very strong. We say that CF bond is very strong when compared to CBr or Ci bond. But still, fluorine is a good leaving group in SNAr SNAr mechanism. This is because of the high electronegativity of fluorine. And because of this high electronegativity of fluorine, it will stabilize the carbanion. The carbanion formed when the nucleophile attacks the substrate. Okay, so the order is usually fluorine, chlorine, bromine, and iodine. That is, fluorine is the best leaving group, followed by iodine. Now, another case, the electronegativity of the halogen, as I said earlier, increases the rate of reaction. That's why fluorine, if the leaving group is fluorine, the reaction will be faster. You have the same electron withdrawing group, but different halogens, such as in the fluoride compound, will undergo faster reaction. Alright, now it's because fluorine is most electronegative halogen, and it will activate the ring a lot more than the rest of the halogen, and also it will stabilize the anionic intermediate. Now here you have the example. You have fluorine and chlorine as the substituents, and also NO2 as the substituent on the aromatic ring. NO2 will be acting as electron withdrawing group. And see here, even though fluorine is present here, it is a chlorine which is being replaced. Chlorine acts as the leaving group here. Now the reason for this is because it is the position of the leaving group which is more important. Or the position of the electron withdrawing group to the leaving group. See here, where the electron withdrawing group is para to chlorine group, the chlorine substituent or the leaving group. And thus, chlorine will be replaced, not fluorine, even though fluorine is a good leaving group. So, the position of the electron withdrawing group to the leaving group is a more contributing factor than the nature of the leaving group. Alright, so you can use this example to illustrate that. Now, what about the nucleophile which comes in? Nucleophile, of course, has a role to play because it is a nucleophilic attack and formation of mesonemer salt, which is the rate determining step. So, high nucleophilicity is important because the nucleophile has to overcome the repulsion from the pi electron cloud on the aromatic ring. So, this is the order of reactivity of various nucleophiles. Alright. As you move down the periodic table, the nucleophilicity increases. That is why you have here the iodide, bromide, chloride. This you can use to understand that the nucleophilicity increases as you move down the periodic table. The exception is even though OH minus is a stronger base than ARO minus, but it is a poor nucleophile. Here you can see OH minus comes after ARO minus. So in this case, OH minus is a poor nucleophile than the ARO minus. So that's an exception over here. Coming to the solvent, effect of solvent. Since nucleophile has to be stabilized and the leaving group has to be stabilized, the solvent must be polar aprotic, or the reaction is usually carried out in polar aprotic solvent, or the reaction rate is enhanced when the solvent is a polar aprotic solvent. Alright, so these are the effects of various factors on SNAr mechanism. So we have seen what the mechanism is, what are the various reactions involved in the mechanism, using this mechanism, and also what are the effects of various factors on SNAr mechanism. Thank you.